You ever notice how the second you click sort by price, a list with a million products just instantly rearranges itself? Or how your social media feed seems to magically know exactly what to show you first? Well, that's not magic. Today, we're going to pull back the curtain on sorting algorithms. These are the invisible engines that bring order to our digital world.
I mean, really think about it. How can some huge e-commerce site sort millions of things by price in what feels like a millisecond? Or how does a gaming leaderboard update in real time with thousands of players? It feels impossible, but it's not.
The answer to all of this, it's sorting. It's one of the most fundamental concepts in computer science. It's the process of taking just total chaos, a bunch of jumbled data, and arranging it neatly. And when data is neat, everything else we do with it becomes incredibly fast and efficient.
Okay, so at its core, sorting pretty much boils down to two main strategies. On one hand, you've got the simple, kind of intuitive methods. They're super easy to wrap your head around, but man, are they slow. And on the other hand, you have this clever approach called divide and conquer, which is just blazing fast. This is the main event we're exploring today.
So first up, let's get into the simple sorts. Now you're going to see this term O of n squared, or ON squared. It's just a fancy way of saying they get really slow, really fast. Think of these as essential learning tools. They teach us the fundamentals. You'd never actually use them in a real modern app, but understanding how they work is the key to appreciating why the faster methods are just so brilliant.
Let's start with a total classic, bubble sort. And the name is just perfect, right? It works by just stepping through the list over and over, comparing two items right next to each other, and swapping them if they're in the wrong order. This makes the biggest values slowly bubble their way up to the end of the list where they belong.
The process is super methodical. You look at item 1 and 2, swap if you need to. Then you look at item 2 and 3, swap if you need to. You do that all the way down the line. After you've done that one full pass, the single largest number is guaranteed to be in its final spot. Then you just do it again. And with every pass, the sorted part at the end gets a little bit bigger.
All right, next up is selection sort. This one has a totally different game plan. Instead of bubbling things around, it focuses on one thing: finding the absolute smallest value left in the unsorted part of the list. So here's how it goes. On your first pass, you scan the entire list, find the one smallest number. Then you swap it directly into the very first position. Boom, it's done. For the second pass, you ignore that first number and you scan the rest of the list to find the next smallest, and you swap that into the second position. The key difference here is it only does one single swap at the very end of each pass.
And our third simple sort is insertion sort. Now, this one is probably the most intuitive because it's pretty much exactly how you'd sort a hand of playing cards. You just build up a sorted section at the beginning, one item or one card at a time.
So you take the next unsorted item and you look backwards into the part you've already sorted. You just shift everything that's bigger than your new item one spot to the right to make a little gap, and then you slide your item right into that gap. And you just do that over and over again until the whole list is sorted. Simple.
So what's the big catch with all these simple sorts? Well, just look at that average case column. They all share that same label, O of n squared. This is called quadratic time, and it's the killer. It's the reason these algorithms don't run the internet. It means that as your list gets bigger, the time it takes to sort just explodes exponentially. If you double the number of items from, say, 10 to 20, the work doesn't just double, it quadruples. And that scaling problem gets out of hand really, really fast. And this just illustrates the problem perfectly. To sort a list of just 10,000 items, which, let's be honest, is pretty small these days, an algorithm like selection sort would have to do somewhere around 50 million comparison operations. That is just way too slow for any modern application.
Which of course brings us to the big question. If the simple, easy-to-understand methods are this slow, how is it possible that our apps feel so instantaneous? How are they handling millions of items without even breaking a sweat?
Well, the answer lies in this really powerful and honestly elegant strategy called divide and conquer. It is a total game changer, and it's the secret ingredient behind all high-speed sorting.
The idea is just beautiful. Instead of trying to wrestle with one giant, messy list, you first divide it. You just chop it in half. Then you conquer each of those smaller halves by sorting them separately, which usually means you just divide them again and again. And finally, you combine or merge those small, perfectly sorted pieces back into one single sorted list. This approach completely avoids that ON squared trap. And this powerful strategy is the foundation for the two heavyweights of the sorting world, merge sort and quick sort. They both use divide and conquer, but they do it in slightly different,
Very clever ways. So here's the high-level comparison. You'll see this new term here, O of n log n. This is our hero. It is dramatically faster than O of n squared. Now, merge sort is kind of like the reliable workhorse. It always guarantees that fast performance, but it needs a bit of extra memory to do its job. Quicksort, on the other hand, is often even faster in the real world and uses way less memory, but it has a potential, though pretty rare, Achilles heel.
So merge sort follows that divide and conquer playbook perfectly. It just splits, splits, and splits the list again and again until it's down to a bunch of tiny lists with only one item in them, which are, by definition, already sorted. Then comes the really clever part, the merge. And right here, this is its superpower. Look at that time column, O of n log n. In the best case, the average case, and the worst case, it is completely predictable every single time. And that reliability is why it's so trusted, even though it comes at the cost of using some extra memory, which you can see over in the space column. Now, Quicksort's approach has a twist. It doesn't just split the list right down the middle. Instead, it picks one element and calls it the pivot. Then, in one very clever pass, it shuffles the entire list around so that all the numbers smaller than the pivot are on its left and all the numbers larger are on its right. So, and this is the crucial part, after that one partition step, the pivot is now in its final correct sorted position.
In practice, Quicksort is often the fastest of them all, which is why it's so incredibly popular. Its average performance is just excellent. But you gotta notice that worst-case scenario. If you consistently pick bad pivots, like if you always pick the smallest or largest item in the list, it can actually slow down all the way back to O(n) squared, the same as our simple sorts. Now, modern versions have clever tricks to avoid this, making it super rare, but it's something to know.
So, after all of this, what's the big takeaway here? We've seen the slow but simple methods, we've seen the blazingly fast but more complex ones. What should you actually do?
And really, it all comes down to this simple, powerful idea. The simple sorts, they're your teachers. They show you how sorting works at a really fundamental level. The fast sorts, they're like your professors. They teach you why clever algorithm design matters so much. But in the real world, on any real project, you use the built-in sorting functions that come with your programming language. They are battle-tested, highly optimized, and usually some kind of hybrid of these fast algorithms. So the next time you sort a playlist or you filter a search result, you'll know about the elegant, invisible dance of logic that's happening in just a fraction of a second. It kind of makes you wonder, right? Sorting is just one piece of this giant puzzle. What other invisible code is out there, quietly running your world right now?